I'm Tom Beutner. I'm the Code 35 Department Head at Office of Naval Research. Code 35 is the Air Warfare and Weapons Department. And I'd like to welcome you to this afternoon's talk or panel discussion on sea-based aviation and force projection and integrated defense. We have a great panel lined up this afternoon with a wide range of things that they've done in their background, including somebody who's done an industrial flight test experiment. A couple of us have worked for the Air Force in the past. One has worked for a warfare center. One has been a department head in academia. And no bonus points for guessing which one, but one of the panelists has also had a lot of operational experience in an F-18 with over 1,000 traps to his credit. He's currently working at OPNAV and brings a perspective of both the warfighter as well as the budgeting process inside the Pentagon. I'm going to spend just a couple of minutes talking about what the NNR is. National Naval Responsibilities are areas where ONR has decided to make a focused investment to maintain the health, currency, and technical superiority of areas that are identified as either Navy unique or Navy driven. And so with sea-based aviation, we don't duplicate the investments made by Air Force or Army, but we focus our investments on those areas that are Navy unique, Navy driven, things like corrosion, interfacing with the deck of a ship, those aspects of aviation that are unique to the sea-based environment. And we do so for a few reasons. If we don't do it, no one else will. And so it's dependent on these investments in NNRs to maintain a robust research capability, to have an adequate pipeline of students who are trained and familiar with the sorts of problems being addressed by the NNR, and to ensure that the S&T products are ready for the next generation of aircraft, in this case, to maintain naval superiority as we move forward. You'll hear about three different sub-areas in the sea-based aviation NNR. The aircraft sub-area, two of our panelists will talk about, and this covers the aerodynamics of both rotary wing and fixed wing aircraft interfacing with the ship, both on the deck and launch and recovery. The structures and materials area, Navy spends more on corrosion mitigation, corrosion prevention, and design for corrosion concerns than the other services do because of the environment that we operate in. Exposure to salt water by all aspects of our ships as well as aircraft. And the third sub-area is propulsion and power generation. Again, some unique naval challenges there, including jet noise reduction. This is a picture actually taken on a flight deck. Person is that close to the exit of a jet engine on board a carrier. That poses a unique noise environment. There are other unique aspects of bolter thrust, the need to do rapid transients on landing from low power to full afterburner. Materials and coatings that get exposed in the hot section to salt water through ingestion of fog and other saltwater contaminants, steam ingestion on launch, and the ability to repair and maintain those engines aboard ship are all unique challenges as well. And so we'll hear about this as we go through the panel. And with that, I want to introduce our first speaker, Brian Holmes-Hansen, who will talk about some of the investments we have in aircraft technology. Thanks.
Thank you very much, Dr. Beutner. And I'll be talking about the flight dynamics and control part of the portfolio for aircraft technology. There are a couple parts. One is the flight dynamics, just the dynamics of the vehicle and how we generate the forces and moments to get us to develop the trajectory, manage the trajectory that we want to do. And another important part are the control laws, and that really gets into the software and the algorithms that we use for generating the software. One part is the architecture of the software and the sensor measurements that you use to estimate the state of the air vehicle, and then how the pilot interacts with the control laws and what commands they're generating. Are they body axis rates, higher level commands for a flight path and things like that. And then to get to the gains that are actually controlling it, there are multiple ways to synthesize that as well. So we're really looking at the basic fundamental 6.1 basic research and then 6.2 applied when you get more towards specific vehicles. In the portfolio, we're very interested in the whole continuum of the fundamentals of the physics and the math of flight dynamics, the applied and how you, and simulation results, but we also want to show data to back up those theories and those predictions of any scaled flight experiments or whatever flight experiments we can do to show increased capability. All the stuff that we do, though, is really tied, I think, very strongly with the mission of the Navy. And at the end of the day, it's to be out there and project force. And to do that, very basically, you have some mass, and you got to get it off a ship and deliver it very timely and precisely to some enemy. So that gives us a requirement that we need to be able to get aircraft on and off a ship. And our directive from leadership is that we need to be ready at all times. So basic flight isn't that hard, but when you're going to do it in very, very challenging conditions, then it becomes hard to really make sure you can handle all the disturbances that can come in very challenging sea states. So these are some of the areas where the flight dynamics and control part of the portfolio is focused. Precise relative navigation, we may not have GPS available, and JPALs are still working on that. It's not really operational yet, but again, we may not be able to get count on having GPS available, so we want to be able to precisely navigate to a ship in a GPS-denied environment. So we're really looking at some sensor technologies and a close collaboration with NavAir. Effectors and sensors, there's a lot of collaboration with Ken's part of the portfolio on fundamental aero, where we're looking at different ways to generate the forces and moments to control an airplane. So fundamentally, we're looking at the fluidics for generating forces and moments. And on the control side, we're saying, well, how do we use that capability in a control law design? What are the right control variables? Is it C mu, kind of your momentum flux, or is it where you're injecting it? So when we bring that into the control system. And then the architecture, again, if you might have heard, there was something that has just gone out to the fleet called Magic Carpet, and that's software architecture for greatly reducing the workload for landing an aircraft on a carrier. And what it does is it basically allows the pilot to interface with the aircraft through a higher level command system. So instead of commanding body axis rates to manage the trajectory, you're commanding a nominal flight path with a delta flight path on top of it. You're really commanding the delta flight path. So it makes it so easy. I'm not a pilot, but I was able to go into the sim down at Pax River and landed on the flight deck. And then, of course, they squashed all my pride because they told me during a STEM event they had a 9-year-old girl come in and do the same thing, and she didn't have a problem either. So but that's a good control law design. If you can make it that straightforward, then the pilots can concentrate on other things. And the key thing about that is you always want to be ready, so it makes it much easier in challenging conditions to accomplish the landing. Multi-body control, the ship needs to stay out there and always be ready. And we're always facing more and more challenging threats. So we want to be able to counter those threats. So we're looking at control algorithms and homing algorithms for how we can best counter threats out there. And lastly, the future is bringing a lot of autonomous vehicles, and they'll be using the flight control algorithms, so once they land on the deck, they're still autonomous. And they have to interact with the deck crew the same way the manned vehicles operate. So we're looking at algorithms on how to properly manage these autonomous vehicles once they get back on the deck. This is a high-level view of the control system, but just to get in a little more, even though it's high level, a little more detail about where we're really interacting and all the parts that we're trying to address the science and technology to better equip the warfighter. Nominally, so you have the aircraft, and it's got its flight dynamics. So we're looking at, again, with like fluidic effectors, how to generate the forces and moments to manage the trajectory. But then sensors, how are you estimating the state of that aircraft? And really, particularly for the Navy, the state of the aircraft relative to the ship. And so there's a lot of investment in those kinds of sensing capabilities. Once you have those sensor measurements, a sensor doesn't tell you how fast the air vehicle is rotating. It doesn't tell you where it is. It'll give you some voltage or some other signals. So now you got to take those signals and apply some algorithms and come out with an estimate of what the state of the aircraft is, where is it going, and how fast is it doing that. Now you know where the airplane is, or you have an estimate of it, and you know what you want to do, and there's some error in there, so So now you have to come up with controls to move your surfaces or whatever effectors you've got to drive those errors to zero to get the airplane to do what you want it to do. So the research portfolio is really addressing all these components of flight dynamics and control. And of course, again, we always want to be ready in any conditions. So all that has to work great, whether you're in a nice calm day or a very challenging day with a lot of disturbances due to gusts. And now that that's all clear, I'll turn it over to Ken Iwanski for Aero.
Thank you, Brian. Thank you, Dr. Beutner. So my portfolio, as it says, is the sea-based aviation technologies, and there's also a focus on rotorcraft as well. So it's not just limited to fixed-wing vehicle aerodynamics. Dr. Beutner referenced a couple of us with Air Force backgrounds. Besides himself, I am the other Air Force guy. I came by way of the Air Force Research Lab, which, as you know, the mission does not include rotorcraft technology, so this has been a fun area for me to jump into and learn all about. So using Brian's other intro slide of depicting the environment, you can kind of look at the portfolio from a couple different focus areas. So I like to look at the upper left side there, the aerodynamic performance and the aerodynamic control. So the aerodynamic control, what I'm trying to look at, invest in technologies that look at the forces and moments that we can generate and force the aerodynamics or the fluid dynamics effects to do what we want to do on vehicle performance. So that is kind of a crossover with the aero performance area itself, because one example would be active flow control, for instance, to generate higher lift increments on a fixed-wing aircraft for carrier landings. But we also have VTOL and rotor wing aerodynamics as well. So from VTOL power lift approach, we want to understand the dynamic effects in that environment with, for instance, dual impinging jets on a carrier deck. From a rotor wing aspect, for instance, there's a V-22 situation that we know through some flow control effects, we can reduce the download, alleviate the download effects just from the hover downwash on the wing. From the aerodynamic performance, we're always trying to gain more insights, pursue an understanding down at the 6.1 basic research level of the fluid dynamics, whether it be down at the boundary layer levels, but also then up through 6.2 applications that would include other flow control mechanisms, but just vehicle performance again, whether it be rotor wing and blade aerodynamics or the VTOL approach, V-stall approach. The aerodynamic interface is what's really unique to the Navy investment area. So here we're looking at everything that goes on that needs to happen to have safe, efficient operations with bringing aircraft to shipboard environments. So I'll have a slide here after this that gets into a little bit more. But we see that as obviously a unique, challenging area of investment for this portfolio. And then lastly, we're always looking and considering advanced or unique concepts. What's depicted up here on the slide is actually an icon image of the TURN vehicle. The TURN vehicle is a program that's jointly sponsored by both DARPA and ONR. And hopefully you may have had an opportunity to go down to the exhibit hall and see the desktop model. If not, I encourage you to go online and Google the ONR DARPA program TURN. But that's aligned to be a game-changing technology program, and the point of that program is to try to get from short deck ship operations to get ISR assets by utilizing a VTOL mode for that launch and recovery aspect, but then also harness aerodynamic efficiency through a horizontal flight mode, all with the same unmanned vehicle. So the aerodynamic interface problem, as I alluded to earlier, is a unique, challenging environment that's unique to the Navy, Navy and Marines. Air Force doesn't have to worry about a landing strip heaving, pitching, rolling, atmospheric conditions atmospheric conditions, but not from separated flows coming off a control tower necessarily. So we have a very complex, highly dynamic environment when we're trying to bring in vehicles, whether they be fixed wing or rotorcraft. So there's a lot of investments to get to the point of understanding all those interactions and not isolated, but in a coupled environment, meaning that we can eventually model the whole environment to safely, to get to a point where we can safely understand through a design process, operating flight envelopes with any of the vehicles, and we don't have to go spend the time, resources, money, energy to try to do that through extensive flight testing. So ultimately, we'd like to get to the high fidelity, real-time visualization, simulation approach for this area. Again, aerodynamics now for VSTOL. We have powered lift modeling and simulation activities. As you know, we have F-35 operations, which has both thermal and aero issues involved. Again, impinging jet interactions between dual jets as well as the deck environment. And what that does, when I say environment, how far out for personnel in the vicinity of that environment. The aerodynamic control bullet there is alluding to, again, what I mentioned earlier about the V-22 downwash effect. We're right now studying implementation of a flow control technique that will alleviate the downwash drag in hover mode that will hopefully then pay off with increased payload, whether that be through fuel or other means of payload. And then lastly, the Vertical Lift Center of Excellence. That's a program that the Navy ONR is joint with NASA and Army, and that really looks to investigate at the 6-1 level through universities primarily, everything rotorcraft or VTOL. Currently, those centers of excellence is University of Maryland, Penn State, and Georgia Tech. Another reason or another offshoot for the VLRCO investment is that tends to be a pipeline for our future researchers. And so we look to harness the investments not only with understanding the flow physics involved within rotor wing and VSTOL environments, but then have the expertise come and stay within the government for the subject matter expertise. And then under aerodynamics with the flow control, there's a couple graphics here. So the upper left is a computational depiction of utilizing a particular flow control technique, but that's at a preliminary design stage, and was looking at trying to understand the geographical placement around the trailing edge flap location. And you'll see the difference with the off and on. The gray area is depicting a separated flow region. And you can see we actually end up getting lift improvements, which in a quantifiable sense, and not to say that data on the bottom left is of the same configuration, but as an example, we have coefficient of lift versus flap deflection as a function of various blowing rates or C-mu coefficients. And what that depicts is that we can extend through various similar flap configuration settings, we can extend the coefficient of lift, the max coefficient of lift, up further, and in a sense gain 20% increase just by putting in a flow control technique in that hinge line area. The upper right is just an example of another wind tunnel test, experimental wind tunnel test, and the bottom right is one example of a technique for active flow control. This is a sweeping jet fluidic flow control actuator, just harnessing a dynamic influence of the pneumatic flow influence. And with that, I will leave it to Bill.
All right. Thank you. So, my portion of the Sea-Based Aviation Initiative is the structure and the materials, right? This is your airframe, your fuselage, your skin surfaces. So it's all of the load-bearing configuration of the aircraft, along with the materials we make that structure out of, and the processes by which we produce, refine, finish, and combine those materials into the structure. And so from a structure standpoint, what we want, not just for the Navy of today, the Navy of tomorrow, and the Navy of the future, that doesn't really change, is we want higher performance aircraft, and we want them to be more durable. And so from an airframe standpoint, higher performance means weight, range, payload trade-offs. And durability means longer service life, more resistant to fatigue. For the naval operational environment, it means more resistant to environmental damage effects, or more maintainable. And some of the ways we're trying to get at that are better understanding of environmental damage mechanisms and developing those into predictive models that allow us to assess durability risk for material selection so that we can more properly match the materials we're going to use to the operational environmental requirements. Tied to that is something I call combined loading mechanics. And this can bridge the gap from something like just a graphical analysis here all the way up into integrated lifing prediction, where what we need to what we're trying to do is to treat the environmental exposure, be that chemical, thermal, exhaust, salt water, whatever, as a loading condition for how it affects our structural life performance, the same way we do with our mechanical loads. And then how we actually combine that into a predictive analysis. This is just one example of how you would match up your loading levels with your crack propagation for a damage progression analysis. Material certification is a big one. One of the biggest impediments to getting higher performing materials out into the fleet is the time and cost associated with fully characterizing and then certifying as airworthy a new material system. And so there's a lot of better analysis, better material predictive capability science that we're investing in to try and shorten the time and cost to get high performance materials into the fleet. Also things like advanced coatings, sealants. This has to do with the environmental effects that Tom alluded to, that we deal with at an order of magnitude more aggressive than our land-based operational sites. And there's different ways to do it. You can design a new material. I just alluded to the cost and the time it takes to get that new material into service. Or I can put better protective schemes into place that allow us to use the same materials longer and with less maintenance impacts. Tied to that is structural remediation. If you've been around at all, you've heard the discussions about aging aircraft, about the fact that our fleet is getting older, about the fact that our new platforms are being designed with the intent to fly them longer and for more flight hours than ever before. And that's not a trend that's going anywhere. What that requires then is that we need to have advanced technology capabilities to remediate damage and to extend the life of aircraft structures. But we also want to balance this with next generational concepts, things like morphing reconfigurable surfaces. We want to be able to implement multifunctional materials, ultra lightweight armor for survivability impacts. So we need to balance the durability aspects with the next gen performance aspects. And that's really where the next generation concepts comes in. So this is just a nominal schematic I borrowed from one of the OEMs. But what it shows is that today's Navy and tomorrow's Navy, we're operating within some fairly well-known material sets. The exact compositions and the exact processes might change, but for the foreseeable future, we're going to have airframes that combine composite materials and lightweight metallic materials, and we need to be able to deal with dissimilar material interfacial behaviors, both from a corrosion and durability standpoint, but also from a thermal and mechanical response standpoint. And this makes it more complicated to do risk and reliability and structural analysis. But ultimately what we want is we want to be able to optimize the airframe structure for the most efficient load carrying capability, the lightest weight, and the longest service life. And the reason for that is we want to improve the operational service life. And there's two ways to do that, as I said. We can implement better materials, or we can better analyze and predict the behavior of the materials we have so that we have less unexpected early failures, damage, or degradation mechanisms. So some of the focus areas within this portfolio, we have them binned in a couple different ways, but nominally you can look at metallic structures, composite structures, and advanced concepts. Within our composite structures and composite materials, we're looking at the damage mechanics, the behavior response, how we characterize things like manufacturing defects, effects of voids and porosity, in-service damage, how we do non-destructive inspection, especially to find early damage initiation before it has become large-scale propagation. Tied to that, though, again, is the materials piece. This is the constituent materials, more advanced fibers, higher strength, more damage-tolerant fibers, secondary strengthening mechanisms to improve the ability of a composite structure to handle three-dimensional loads the way a metallic structure can, but also the resin chemistry from which we get a lot of our environmental and thermal properties. And then tying that into some advanced manufacturing techniques. One of the biggest challenges in composite materials is the cost and the associated defect rate of manufacturing these constructed composites. And then on the other side is the metallic structures as well, right? We don't want to forget the other piece of this. Again, I alluded to the material selection, matching up the proper material for both durability and performance, tying that to service life prediction. Ultimately, one of the biggest things is being able to control interface behavior between dissimilar materials to reduce the environmental damage impacts so that we can then field more durable, more maintainable aircraft. And if you've ever been aboard a ship or had a chance to do a walkthrough, it's a very constrained environment in which to try and maintain some very complex, very high technology assets. And tied to that is the advanced materials and processes. This is your inspection, your coatings, your sealants, but we're also getting into things like galvanic isolation barrier layers that can just decouple these dissimilar materials so that we remove a driving force for damage. And then that's what I had, and I'll turn it over to Knox for the propulsion program.
Thank you, Bill. Today I want to discuss the power propulsion thermal management part of this program. First and foremost, I'd like to invite those people who are interested in this area to come talk to me. I won't be able to give a very extensive overview of this, so most of what will be useful is to have one-on-one discussions. So I invite you to come see me after the meeting or send me an email. I want to discuss those areas of power and propulsion that are Navy unique and Navy driven. As Dr. Beutner said, there are other people in the Army with helicopter engines, the Air Force with fighter engines, as well as NASA and the FAA that deal with commercial engines. So we really focus on those areas that are Navy unique or Navy driven. Some of the areas I'm interested in, and I will tell you the interest and why these are Navy unique or Navy driven. One is the component coupling. Navy engines are very constrained. They are smaller and they have very complex flow paths, and so to get high power density you really need to put the components together, and so there's a lot of component coupling. The inlets, the fans, the core compressors, the combustors, the turbines, the afterburners, and the nozzles are very close, and there's a lot of interaction, and you get in a lot of problems with that. And so the physics of those viscous and potential interactions are very important. Isolating those components. I've got a program on multi-physics sprays and their controls. Obviously, this is very important for combustion, but there are other applications such as additive manufacturing where these are important. Doing some work on high power density combustion systems, pressure gain combustion has the potential to increase efficiency and hence range and power density. And also have a program on mesoscale combustion, so very small combustors. This potentially can reduce the length of an engine. If you look at an engine cross-section, about 60% of the length is in the main combustor and afterburner. So ways to reduce the length are very important for this integration problem. Again, engine airframe integration. Inlets in naval systems tend to be S-ducts. It generates secondary flows and thick boundary layers, so the ability to control that either with passive design methods or active flow control, sweeping jets or other things are very important. This is true for subsonic flow, but also supersonic flow when you have shock and shock boundary layer interactions. So doing a lot of work on that. A component to that is the interaction of the distorted duct flow with the engine fan. So designing distortion-tolerant fans, having high efficiency when they have flow structures in front of them, operability, that really means throttle ability and stall margin, and aeromechanics, fatigue and other problems there. Also, probably one of the biggest areas emerging in future engine airframe integration is the thermal management. How do you collect heat, either within the engine for cooling air and other things, or from other components, distribute it at different thermal fluxes at different temperatures, and rejection. How do you get it off of the aircraft, either through the engine ducts and other methods? So these are increasingly difficult problems with the thermal management. Fluid mechanics of turbomachinery. One of the things that's very important is to get very high stage loading, and the reason is to make the spools smaller, reduce the moment of inertia. As Captain Brophy would tell you, if you miss the wires and have to bolter, you really want your thrust and you want it quickly. So there are no other applications where you really want to go from a near flight idle to full power in a couple of seconds. Pretty important. And one way to do that is to have fewer stages and higher stage loading. And what really limits that is tip flows. And so we're looking at the physics of tip flows and how to improve stage loading. Active clearance control is one method. Another method is casing treatment. So advanced casing treatments and understanding the physics of it. They've been around for a long time, but people really don't know how to design these things for specific applications. Fans have certain designs. First stages of core compressors are different, and the last stages, people try them till they work and then they stop. And I'm really trying to understand how these things work throughout the machine. One of the big areas going on to jet noise reduction, as Dr. Beutner indicated, is this problem of jet noise, near field jet noise due to jets on the carrier decks and the personnel in near proximity to that. These can generate noise in the neighborhood of 150 dB. These far higher than any other jet noise problem that you'll see in industry. A lot of commercial footprints may be 80 or 90 dB, so several orders of magnitude difference. We're really interested in the physics, how the noise is produced, how to predict it with codes or physical models, and we're doing a lot of high fidelity development in here, particularly large eddy simulation. Sorry for the acronyms there, but doing some work on direct numerical simulation to better understand the physics, and large eddy simulations that can be used for understanding the design codes. Looking for methods to reduce the noise. Chevrons are something we've tried, both physical and fluidic injection, and really looking to transition these to practical applications. NAVAIR has a program to look at this in the F-18 to reduce noise. And also doing work at the bottom in small propulsion. This would be either weapons or you could say medium size for helicopters. And so there's some unique areas, potentially looking at recuperated engines to get better fuel efficiency, and other aspects, oilless bearings, so going to foil, hydrostatic and hydrodynamic bearings, and looking for other advanced concepts for long duration flights, for persistent surveillance and other things in small engines. Here is a graphic, again, showing a person in the near proximity of a jet, and the modeling of that, computational fluid dynamics on the top right hand, along with some experiments done at NASA Lewis. Kylis at the Naval Research Lab, we funded him to do a code called Genre, which is a large eddy simulation, very efficient code for predicting those high-speed supersonic afterburning plumes and the noise they generate. Finally here, I do work in materials, mostly hot section materials, but I have Dr. Dave Schiffler from Code 33, who does both ship gas turbine materials as well aviation. There are some differences, but a lot of similarities. And his focus area has been in composites, CMCs, ceramic matrix composites, 6-SiC and carbon-carbon, going up to 2700 and beyond for uncooled parts. And he's got a long history of working with thermal and environmental barrier coatings and looking at damage. These CMCs, just as composites on airframes, when they get damaged, they propagate. They're not as forgiving as some metals with plasticity. And he's also doing some work in high enthalpy alloys, multiple principal alloy compositions. So I encourage you to talk to him. If you need a contact, please get to me and I'll forward your information to him. So anyway, thank you, and I'll turn it over to Captain Brophy for a view from the fleet and OPNAV.
All right, good afternoon. Kind of as Tom mentioned, I'm the ugly duckling, or the one that's completely different. In fact, if my roommate from college were here, he'd kind of be laughing me off the stage, saying the emperor has no clothes. So it's quite an honor to be able to join a distinguished panel like this. Yes, I'm going to bring kind of the operator perspective to it all. I'm also going to bring the OPNAV perspective to how we take all the science and technology that you all help develop and the team here helps develop and puts it in so the warfighter out there is able to win wars. So, good afternoon. I'm Rich Brophy. Call sign is SNAP. And I'm going to talk about the next-gen air dominance that we have started, which is an analysis of alternatives as we start looking at what the future of aviation is going to be. So if you look actually on the best way to probably describe it is to look at the United States Navy TAC Air inventory, where we stand today and where it's going to look like in the future. So if you have this vertical axis here is Navy TAC Air squadrons. Along the bottom is basically along the top is years. So right here is F-18 A through CD, older aircraft. Obviously, clearly, we are retiring them as it goes along. We've bought a whole bunch of F-18 EFs. Is this line here. We have already looked at extending the service life of these F-18 EFs, so that's the next line right there. The top line up here is the F-35 and then any additional F-35s. The yawning gap that you see developing out there, which is roughly around the 2030 time frame or so, is the next-gen air dominance. That is the replacement for the F-18, EF, and EA-18G Growler. So once those airplanes go away, we have to replace them with something. And so what we look at right now is we're looking at it from what are the mission areas currently that those airplanes currently have. I have them listed right here of note, things like air warfare, electronic warfare, strike warfare, kind of all the things when you're like, wow, what does a carrier air wing do? This is the strike fighter power of the carrier air wing. And so when they go away, how are we going to replace it? We are looking at it from a holistic standpoint, because when the Navy fights a war, we don't fight it just from a single airplane, we fight it from a strike group perspective. So we're looking at it from a complete strike group perspective, or as we like to say, a family of systems potentially can replace some of the capability areas that are here. It is not lost on us that AI, unmanned, it's coming and it's out there, and we need to be able to incorporate that into what we're looking at. The trade space is completely wide open as we look at what is going to replace those airplanes. We've started the study. We were working a study in conjunction, not kind of parallel with the Air Force. The Air Force is doing a penetrating counter-air analysis of alternatives. We're doing our NJAD. We're also looking at the surface side, which is doing a surface look as well as what the surface Navy is going to look like in the future. In the end, we want them all to be able to marry up, because in the end, we fight as a joint force in order to win our wars. You can see where the timelines and when we've started and where we're going. So how's the Navy kind of breaking it up? Well, the team has broken it up kind of in an A through D categories as we look at it, and those A through D categories start from as simple as status quo, we don't change a thing. How will that look like in the future? As scientists, of course, they have to be able to rule that out. As the common man guy standing up here, I'm like, of course it's not going to work. So obviously we'll look at it, we'll probably rule out A initially, but that is you just do nothing. You just keep where it is, and we just keep with the airplanes we have. Clearly they're going to retire at some point, so that one to me doesn't necessarily hold that much water. But as you go down further, you get into transformational capabilities. Be honest, I work on budgets and stuff as well, so I tend to think of that as cheaper to more expensive. So as we look at these capabilities, the one thing that keeps coming up time and time again are numbers matter. We got to be able to have enough airplanes out there. I mean, in the end, when these airplanes retire off of a carrier, that's 24 spots that are shadows right now on an aircraft carrier. Something has to replace them, because in the end, numbers matter. Navy tends to fight our wars away. We tend to fight not as the home team, but as the away team, so we bring what we bring. So as we look at it, what are we doing? Next is what happens if we just increase our inventory using programs of record such as the EF and G, or just increasing our F-35s, and then keep the program of record of weapons. We look at that, then it gets a little bit more expensive, where you say, what happens if we just increase the capabilities of the EF and G or F-35? Will that be able to meet the gaps of the future in the 2030 timeframe? And then the final one is, well, what if we just need to do a completely new start? And we're looking at that as well. But clearly, the team that we have down at NavAir that's looking at this, about 60 or so folks, very smart and intelligent, but they don't have the knowledge of what is out there in academia and industry, and that's where you all come in. There's a CRADA that they have established with industry. If you haven't reached out and talked to our NJAD team and you have ideas on how the Navy can fight better in the 2030 timeframe, by all means, please reach out. It's a family of systems. It might not necessarily be an aircraft. It might be an aircraft, another system, and maybe it's another system that's on a surface ship. Family of systems. So if you have ideas, by all means, please reach out. It's very important that your ideas are folded into what we are thinking. Timeline for it. We started it about a year ago. There's 6 steps to the process that you see up there. Where are we right now? If you can't see it from the back, we're about right here. So we're generating alternatives. So we've gone through the decision framing and developing and objectives and measures, which really can be the hardest part. So when you think about it, when we said, hey, we are looking to do a family of systems, take a step back and think about from an analytical perspective how hard that really is to wrap your arms around all that. And so we're now at the point where we think we've wrapped around our hands about the whole what a carrier strike group should be in the future, the threat that is out there in the future. And now we're at the point where, all right, can we lop off some of those angles so we can start focusing it down into, in the end, will be a material solution in order to fix the gaps that are out there. I said we're using 6 steps. Set-based design is how we're doing it. We're trying to bring in the latest, greatest tools that are out there, such as data visualization, especially when it comes to performance and cost analysis. So kind of in closing, NJAD study that we're looking at in order to place the E, F, and G, and it's going to be sometime in the mid-2030s or so on when those start retiring, and so we need your help on that. Looking at it from a family of systems perspective, and bottom line, what we're looking to do is we got to create something for those airplanes for those mission areas that we lose when those airplanes retire, something has to fill those in the end. Because in the end, we fight away wars, and we got to be able to win the war when we're away. Standing by for any further questions.
So we have just a few minutes, but I want to take advantage of this opportunity. As I look around the room, we have a lot of researchers who are looking for problems to work on, and we've got a panel that has got problems that are looking for solutions. Is what you call an opportunity-rich environment. So I'd like to ask each of the panelists, as you think about the portfolio and the range of areas that you're working on, if you have a top 10 list, or maybe in the interest of time, a top 1 or 2 list of areas where you're really looking for a solution, a new or different way of doing things, or a better way of doing something that we currently have as a limit in our processes or our capabilities. Start with Brian.
Thank you, Dr. Beutner. Certainly, it's very important, the networked and homing guidance algorithms for threat engagement, interceptors, next generation interceptors, that's a really important one. And then, of course, enhancing the capability of the warfighter for operating in the maritime environment under extremely challenging conditions. So that includes next generation air dominance, looking at how you would generate the forces and moments to really precisely handle tailless aircraft, and then how you would operate in GPS-denied environments for precision relative navigation around ships. Those are, I would say, that's some of the top things that we're really focused on right now. Should I go down there?
Yeah, so Brian just touched on one of the ones that I failed to address earlier, and that was from the flow control aspect, generating forces and moments, looking at it not only from legacy aircraft, how can we do things better to improve performance, but looking again towards NGAD and most likely something that might be tailless. How do we best come up with a design that we can control with minimal minimal vertical tails, surface controls, through whether that means active flow control, but not only longitudinal pitch control, but lateral stability as well. The other one, the biggest one I think right now within this portfolio is that dynamic interface environment. We want to operate not only efficiently, but safely. And to the point that we can go ahead and mature simulation techniques that get us to the point that we have that confidence and we can validate these simulations to have confidence in expanding flight operation envelopes. I think that's a big challenge, and will continue to be an investment area within this portfolio. Top 2 right there.
All right, so I think from the airframe, the structures standpoint, the upside for me is that no matter what NGAD looks like, I'm pretty confident that air vehicle will have a structure. It'll be load bearing, it'll be made of materials. So the challenge is really kind of propagate across the platforms. For me, the top one in metallic structures is structural mediation. Harnessing additive manufacturing and advanced repair capabilities to extend the service life of whatever that platform of interest is probably my top one. And in composites, I think it's marrying up new material development for three-dimensional load carrying capability and rapid certification would probably be the top 2 enablers for whatever NGAD ends up looking like.
I would say one way or another to get higher power density or specific power, that is power per unit volume or unit frontal cross-sectional area of the inlet, or power per unit weight. So however you can do that or contribute to my program in that area would be most appreciated. That also, not just the thrust, but the thermal management. So being able to scale up the thermal rejection capability by an order of magnitude in a reasonable volume or weight. So if you scale up a 5th gen fighter and you say how big and how much does the thermal management equipment weigh, it will eat the entire payload of a fighter. So we need to do much better than that. So any ideas you have to improve either reduce the weight or reduce the volume of the machinery, turbo machinery combustor, or the thermal management is really what I'm most interested in.
Okay, once again, I'm going to take it slightly differently. I won't take it to that degree, but when I look at it, I look at we have to be able to win in a high-end fight. What's out there in the future, it's going to be high-end. The proliferation of weapons is spreading throughout the world, so it's got to be able to win in those fights, including all the changes and structures that were just mentioned. When I look back and reflect on my career, the things that I wish we had, and I look at the limitations of a carrier air wing right now, range is a significant problem with the carrier air wing and how far it can go out. I tend to think of it not just as range, but as reach. So not only how far can my airplane fly, but how far can my weapons go on top of that. So truly, it's about the reach of the air wing that kind of matters. Reach also gets into, obviously, propulsion. When we look at propulsion, I'm looking for efficiency. The longer I can fly without having to go get gas, the better. Gas is just another one of those things as a strike group that you have to be able to put airborne. That's one less, when I do that, that's probably one less airplane that's able to have weapons on it. And what matters is when you have weapons, not me passing gas. So range matters. Additionally, speed is, a lot of aircraft out there have speed. We'll have to potentially fold that in. We haven't had speed in a naval aircraft really since the F-14 has retired. It's something we probably need to consider in the future. Final couple things to think about would be, as I said, numbers matter, which kind of gets to the cost. So the more we can drive the cost out, the more of these platforms we can buy, which will just make us a more lethal force.